Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our calculus series, and we're going to do some exercises on Taylor series, section 1. So let's just hop right into it. So last time we talked about Taylor, or no, not Taylor, tangent. We're talking about tangent lines, right? We talked about tangent lines and how to bound the error, right? So we went through some problems. We were able to determine some formulas here, such as this one. So this is what we call the tangent line approximation. It's basically a line at that point, and then we take its derivative and stuff like that. And then we also talked about how to bound an error of the tangent line, which is, where was it? Here. So we have this one, which is equal to, or less than or equal to this thing. So everything that I've enclosed in a red box is what we're going to be dealing with in these exercises. Okay, so let's just hop right into it. So first we want to find the first Taylor polynomial, and we're actually gonna assign, some stuff here. This is t sub 1 of x, right? This is gonna be some function f of x, e to the x. And this is based at b equals 0. So here we're just gonna use the formula, right? Use formula for t sub 1 x. So the formula is t sub 1 x. This is equal to, or actually, let's just copy out the formula that we got. F prime b, x minus b, added to f of b. Right? So that's the formula that we used. Yes. Right? Or actually, to be more, let's just use this. There we go. Much better. Okay, so let's actually do that. Actually, no, let's just use the y. Why not? Because I don't know what that is. For first Taylor. Right, so b is 0. So just to copy that formula, it's f prime of 0, x minus 0, plus f of 0. So I need my derivative of this thing, which is just e to the x again. And so my f prime of 1 is just e to the, or oops, f prime of 0 is just e to the 0, which is 1. And my f of 0 is e to the 0, which is also 1. And so this is just y equals x plus 1. So that's the formula, right? X plus 1. Okay. See if you actually got that. Oh, doesn't show in. That's funny. Okay. Yes, so it's x plus 1. Oh, we could have used the t notation. We could actually use that. T sub 1. There we go. And then we get this thing here. Yes. Let me just move this. Okay, that's nice. So it's, yeah, it's 1 plus x. And then we want to use the tangent line error bound to determine which of the following are true, right? Let me take a screenshot. So which one of these is true if we use the tangent line error bound? It's going to be in all examples. So what's the tangent line error bound again? The tangent line error bound is, so if we just copy, or actually, I think I memorized, no, I don't memorize it, I'm kidding. So we have the absolute value of my function minus its tangent approximation, or tangent line approximation, less than or equal to m divided by 2, x minus b squared. Right? I don't want to go into all the deriving, because I don't need to. I just need to know what this is. Okay, so let's actually plug it in, right? Yes, so we can say this is, this thing here is the same as my first Taylor polynomial. So I could say that. Yeah, because this one's just equal to that. Okay. And then let's just plug it in, right? Like let's see what this is. So f of x minus my first Taylor less than or equal to, what's my m? I don't know what my m is. Nothing here says anything about an m. Hmm. Is there a way to get m? Second derivative. Oh, so we could get m by getting the second derivative, right? And then once we get the second derivative, now we can use this idea. So we want to get the second derivative and get its absolute value, right? And then we plug in one of them, doesn't really matter which one, because it should be the same at the end of the day. Okay, so here we calculate this thing. And so what is this? The second derivative of my original function is, it's really just this again, right? And then if we were to take its absolute value, well, again, it should be the same thing, right? And then if we were to get its, it should be less than or equal to m. And so I just plug in the interval here because I could. So if we plug in this -1 or 1, I don't think it matters too much. E to the 1 Or e to the negative one. I don't think it matters. Zero point. Oh, it does matter. Oh, shoot. Uh-oh. So it does matter. Okay, let me see how they would answer that type of question. Okay, let's just do this step by step. So how do we calculate the error bound? Let's use this formula here, right? We also say this is an absolute value. And then we want to calculate the second derivative here, which actually just gives me e to the x. And then we just plug both values in, right? So on interval -1 to 1, e of x ranges from, say, e to the -1, which is around 0.3679, all the way to e to the 1, which is around 2.7183. And so, yeah, the maximum value of this thing is e to the 1, right? So m is e to the 1, or which is the same as e. And so that's my e. And so also b is 0. So here's where we kind of just use the formula. So we say, okay, well, my error bound is m divided by 2 x squared. Now, why is it x squared? Well, that's because x minus 0, right? And then on the interval -1, 1, the maximum x squared is, well, it's 1, right? So again, here we plug in -1 and 1. Actually, funny enough, they should be the same, right? And so, yeah, that's the final answer. So the bound should be at most e half, right? So at most, it should be e to the half, which is around 1.35915-ish. And so let's try to evaluate the other bounds. So yes, so first we try to solve it, right? If we evaluated the other bounds here, Let's actually just do that here. So this one's correct, right? I should here because the air is exactly there. This one, 3/2 is around 1.5. And this is true, right? Because the air band is larger. So if it's larger, then we also say it works, right? So basically, we're trying to find the maximum it could get. And then this 1/2 is not true because it's less than the maximum error we could get, which is a half, right? Let me, I'm a bit confused here because I thought, anyway, I'm going to check something. Because why is this true and then this one's false? Since the maximum we could get is around 1.35, then how come we allow 1.5 if that exceeds the maximum? The actual error is less than. Oh, then it is always true. Okay, so if this thing is less than 1.3, then it's definitely less than 1.5. So we can say it's less than, the error is less than 1.5. The tangent line error bound. And then here, this is a half, 0.5. Well, this is less than the max error, right? Okay, I see. I see how it kind of works. So we have some error. It's at least this. And then we say this is true because it exceeds this, right? So we're sure that this is less than this. We're sure with this inequality. This one, are we sure? Not really. No proof to say, right? But the moment it exceeds, then we know that's true. So I would say those two are true, and then the last one's false. Let's see if we get it. Nice, got it. Okay. Yeah, we're gonna do like, oh, okay, let's do a couple more. Right. So number two, so again, we're being asked to find the Taylor polynomial, the first, or what do we call this again? First Taylor polynomial for some function f of x. And I think this was natural log 1 plus x, and then based at b equals 0, right? So again, we use that. So we want to use the formula. So find, so we have d1, and then we just go for the the thing here. So we have f prime of 0, x minus 0, plus f prime. Or no, not f prime, f of 0. Right? Because that's the formula. And then from there, well, now we say, okay, my f prime at x. So here, let's generalize it first to x. This is 1 over 1 plus x if we take its derivative. We do a chain rule, this just becomes 1. So same thing. And then if we plug in the 0, well, now this is basically 1. And then we have f of 0, which is the natural log of 1 plus 0. And so, oh, this is just ln 1. That's 0. And so our final answer would be f prime of 0 is 1. So we have x. That's it. Is equal to x. And then if we again use the tangent line error bound on some interval, so there, which of the following is true for all values of x in I, or in this particular interval? So again, we just go through the steps. It's really all about going through the steps. So we calculate the absolute value of the second derivative of my function. And so if this were the first derivative, now I want to find the second derivative. So second derivative would be this. Let me square that. Right? And so here we get a 0. Here we get, this one's 1. And so here we get minus. So we get that. And then we get absolute value, so that completely takes out the negative. I square this thing. And then from there, once we get that, we say it's less than, or shoot. And now we plug it in the interval. So on interval, where does it range from? So that we can find our m. So this thing ranges from negative 1/3, 1/3. So this is, let's do the minus first. This one's 3/3, 2/3 squared. Yeah, 3 minus 2/3, 4/9. I'm gonna do 9/4. Or what is this around? It's 9/4. 2.25. Okay. 2.25 all the way to 1, oops, 1 plus 1/3 squared. Well, that's just 4/3, 4/3 squared. 16/9, 9/16. And that's gonna be, oh, so it's the other way around. So, so we have that. So my M is actually the greater one, 2.25, right? That's my M. And so now using that, you want to use the M by putting it into the formula. Did I just say use formula? I want to say use formula for error bound. So that's going to be, what is this? Yeah, the absolute value of this thing. Or shoot, no. Oops, my bad. My function minus my first Taylor polynomial less than or equal to my M divided by 2. And then I think this was, what was my B again? Shoot. Oh, my B was 0. I have this thing again. Right? So same idea. And then from here, on this interval, I find the maximum of whatever's inside this thing. So mm, so on this interval, the max of this thing is, well, actually, even if I plug both of them in, it would just give me 1/9, right? Because I just plug it in here, I get 1/9. Great. So what does that do now? Well, once I get that's 1, I just have to plug it in here, right? So I have this thing. And now this should give me some value. So, oh, it actually gives me an exact value. That's funny. 0.125, 2.25 divided by 18. So my error is at most 0.125. I can expect an error like that. Now, if I get something that exceeds, then that's true, right? Is this, it should, as long as it's less than or equal to this, then anything that's less than or equal to this should work. Anything that's beyond shouldn't work. Or no, no, no. I'm kidding, I'm kidding. I meant if I do a bigger error, then that is sure to work, right? There has to be a way I can write this so that I'm not. Oh wait, is there like a oh here, let me just do a note. If it's less than an error, then it's sure that it's always less than a bigger error. So if we had a bigger error, then it's always sure that it's less than. So that's like basically what makes this statement true. So here's less than or equal to 0.125. If I were to have a bigger error, it should definitely be less than this. If I had a smaller error, then we're not sure. So it's all about certainty. How sure are we of the error, right? So if we went back to the Ken example, right, how sure are we that Ken's son drove 25 miles? And it will give us some error, right? So that's the idea behind this thing. Okay, now going back to the example here, how sure are we? What was it? So my error is less than or equal to 0.125. 1 divided by 32 is, oh, this one is 0.03125. 1/8 is 0.125. So if my error is less than or equal to 0.125, then it's sure to be this one. So this is true. Now, how about this? Is it, so it's less than this? Is it sure to be less than this? Well, this one's less, so we're not actually sure. And so not all of the above, also not none of the above. So it's actually just this, right? Of course, I'm gonna check. I don't know if I got the right answer. So the idea is I try to answer it first, and if I get it, then cool. If I don't, then that's too bad. I'm using a, oh shoot, I took out the homework. That's not good. I accidentally took out the homework. I pressed X. Oh my God. Okay, let me just go back. 15. Oh no, I'm in Taylor Notes. So this is Taylor Notes, section 1. Cool, cool, cool. Really all about academic math is mastering the patterns. Once you get the patterns, you're good to go. Which is too bad. I really like it that way. Let's see. Yeah, so I got the absolute value. Maximum error is 2.25, right? And so I apply that error bound formula. I compare the options. This one's not guaranteed because it's too small of an error. Yes, there's only one correct answer, which is that. Okay, let me see if I got it. Got my eyes. Nice. Okay, one more. Oh, true or false question. I don't like a true or false. Again with the tangent line error bound. Oh, okay, now we have some complicated stuff. Anyway, we'll see how we answer the other ones. Okay, number 3. So here again, we find the first Taylor polynomial for some function f of x, which is equal to 7 sine 3x based at b equals 0. And so this is, okay, we have that thing. So we have f prime of 0 x minus 0 plus f of 0. So here I try to find my derivative. And so that's 7 cosine 3x times 3. That's 21 cosine 3x. And then my f prime at 0 is 21 cosine 0. Cosine 0 is 1, I believe. So this is 21. And then my f of 0, that's another thing. F of 0 is 7 sine 0. Sine of 0 is 0. This is 0. And so my thing here is just 21x, right? So the first step is finding the first Taylor polynomial, t sub 1 of x. Which I think is usually the easiest part. Okay, now I do a true or false, so I only have one try. So I'm a bit scared I don't get this one. I'm gonna make sure anyways that I get it. If I don't, it's okay. Okay, so now we have this idea or question. We want to find the tangent line error bound to bound this particular error on this interval. And now true or false. Is it less than or equal to 0.315 for every x in this interval? So we basically just try to do the same thing that we did earlier. We calculate the second derivative and we take its absolute value. So calculating the second derivative, well, that's just gonna be, this one is 21, so we do a subtraction, minus 21 sine 3x. We plug out the 3, so that's 21 times 3, that's 63. So that's actually minus 63 sine x, or sine 3x. And then if we get my absolute value, well, that's just positive 63. Or everything just turns positive pretty much. And then from here, what happens? Well, if we, so say we have this, what was the next step? We calculate, I'm pretty sure we just calculate m here, right? Okay, so that's the next step. We want to calculate m. So on this particular interval, but basically all we're doing is plugging in. Negative 0.1 all the way to 0.1. So on that interval, we want to, we're trying to do again. Oh, we just want to plug it in, the function, right? So we have 63 sine 3 times this. Does that give me a number? Sine of 3. Oh, okay. So we got around negative 18.62. And then let's plug in the other one. Now this should give me a positive number. Oh, it actually gives the same thing. That's funny. So on those two things, we say that m is equal to this thing. Or let me keep the whole thing intact. Why not? So just to keep the whole thing intact, I'm gonna say 6177730 We also have that. 3 sevens. So M is equal to that. I want to be as precise as I can. I wanna avoid making too much errors here. Okay. Great. So that's M. So that's the first step in calculating this. We want to find the absolute value of my derivative, find M. Then after finding M, we use the formula for that error bound. This is gonna be the world. Yeah, so it's just my function minus my first Taylor polynomial less than or equal to my M. So in this case, it's this thing. 3 times 0.1, what is that gonna be? 0.3. Divide that by 2. Then we have my absolute value, X, minus, where's it based at? Oh, so it doesn't say where it's based at. Oh, it says it's at 0. Oops, my bad. I think everything's just based at 0. Yeah, so it's all based at 0. And then here I tried to find what this X is, right? So I just plug in the X values. So on this particular interval, negative 0.1, 0.1. Well, that's where we plug in the X. Maps. 0.1 squared is 0.01. Right? Because I just plug it in. And so that's where I solve for it. So once I get the max, I just multiply it, and then I see where it goes. Okay, let me actually try to, so this is like around, yeah, 18.61777, 302 divided by 2. Yeah, I'm trying to be as precise as I can. I could keep a couple of decimal places in, but here I'm going to keep everything. And then this is around, like, yeah, so 0.093088865. Cool. Okay, I should stop. Yes. So the maximum error it could get is this. Now, is it true that we can have an error like this? Well, yes, yeah. So this is true. Since error bound is less than or equal to about 0.093. So for sure that that's the maximum. If we have something bigger, then we're sure that it's less than, right? Definitely we're sure. That's the idea. So I would say that's true. But again, we'll see if we get this right. I have a feeling I messed up a step, but I don't know. There's always a way to check. That's using AI. Anyway, okay. I mean, at least I did it first. Okay, 21x. So we did get that first part. Now this next part is going to be tricky. Tricky in the sense that I only have one try. What is this? Oh, I only have like, okay. So after this, I'm gonna go for a bit because I have to buy food. I'm gonna come back though. I'm gonna stop the video after this problem. 0.315. This one's higher. Yeah, so it's around like 0.03. Yeah, yeah, it's true. I would say it's true. So if we get, I'm a bit confident that we got that. Nice, we got. Okay, so I have like two more items to go, but for now I'm gonna stop the video here. I hope you guys learned something, or at least an application of what getting the error bounds of a tangent line is, how to approximate it at some given point. It's really just a derivative concept, calculus 1 concept. But yeah, I hope you guys enjoyed, and I'll see you all in the next video.